Hello friends. Third topic on CCTP7 section first, inorganic chemistry paper second. The old name will be CHI 230. The first section is the coordination chemistry. Second section is the bioinorganic. So third topic for coordination chemistry will be magnetochemistry. So to calculate the magnetic moment, different formulas are there. To calculate the magnetic moment, different formulas are there. So in my first video lecture, I try to explain the different formulas that are used to find out the magnetic moment. The first formula, I think everybody knows that. The spin only magnetic moment. Spin only magnetic moment. It is denoted by symbol μs. And it can be calculated by using equation μs is equal to 4s into s plus 1 or is equal to square root of n into n plus 2. Whereas is spin quantum number and n is number of unpaired electron present in d orbital. So commonly by using number of unpaired electron, we can find out the spin only magnetic moment in Bohr magneton unit, that is a Bm. Bm means Bohr, M is magneton. So it is unit of spin only magnetic or all magnetic moment is Bohr magneton. Actually, if we consider number of unpaired electron in d orbital, it may be 1, 2, 3, 4, 5, and respective magnetic moment, Ms magnetic moment, I have also summarized here. If one unpaired electron is there, the Ms is 1.73 Bohr magneton. If two unpaired electrons are there, 2.83 Bohr magneton. Three unpaired electrons are 3.87, 4.90, 5 unpaired electron, 5.92 Bohr magneton unit. If zero unpaired electrons are there or no unpaired electrons are there, then that type of complex is considered as diamagnetic. If complex contain 1 or 2 or 3 or 4 or 5 unpaired electron, then that type of complex is considered as paramagnetic complex. Second way to calculate the magnetic moment, it is rarely used, that will be the orbital magnetic moment denoted by symbol μL, and μL is equal to square root of L into L plus 1, where L is orbital quantum number. Third type of magnetic moment will be spin and orbital magnetic moment. It is denoted by symbol μSL is equal to square root of 4s into s plus 1 plus L into L plus 1, where s is the total spin quantum number, L is the total orbital quantum number. Okay, by using equation spin only magnetic moment, we can calculate the magnetic moment of d orbital. Same equation we cannot use to calculate the magnetic moment of f orbital, rare earth. And therefore, magnetic moment for rare earth, that lanthanide and actinide, can be calculated by using equation μj is equal to g into square root of j into j plus 1, where g is Landau splitting factor and j is total angular momentum quantum number. We know that how we can be calculated mod of L plus S to mod of L minus S. With the help of this equation, we can find out the total angular momentum quantum number. And the fifth equation or formula to calculate the effective magnetic moment denoted by symbol mu effective is equal to mu s into bracket 1 minus alpha divided by 10 dq. Mu effective is the effective magnetic moment, mu s is the spin only magnetic moment, 10 dq is the crystal field parameter, alpha is called as orbital contribution. If E type of ground term is there, then value of alpha is 2. If T type of ground term is there, the value of alpha is the 4. So I have to decide whether it is A type or the T type of ground term is there, and depending upon that we can find out the value. So if we consider here alpha orbital contribution, for E type 2 value I have to take, and for A type I have to take the value of alpha as 4. Then here lambda is there, it is called as spin orbital coupling constant. If cell is more than half filled, cell is less than half filled, depending upon that we have to select the spin orbital coupling constant value. If cell is less than half filled, we have to select the spin orbital coupling value as positive, and if the spin orbital coupling value is negative, we have to select the cell more than the half filled. So in this way we have to select the lambda values. Okay.